Hey everybody. Today we're doing some regression analysis using R. In particular, I want to do a little bit of variable selection. I'm going to use backward stepwise selection today. I've already loaded up Tidyverse as well as a couple of other packages that I'm going to use. I'll talk about Broom and Galley as I get into this. I'm going to be working with an example from a book I've been reading lately, which is Regression Analysis by Example by Chatterjee and Hadi, and that's got a bunch of useful stuff in there. I'm looking at what they call dataset P060. I've already read it in. I have called it performance, and in the version that I have here, I've given the columns some more sensible names. That's the one I'll post to my GitHub, but again, this is taken from that book. Here we have 30 observations on 7 variables. So what we're seeing here are ratings of a supervisor by their employees. We have the overall rating of that supervisor. That's going to be our response variable of interest, the thing that we want to explain. And then we've got 6 potential explainers. Handles employee complaints, no special privileges for employees, space for learning, raises for performance, not overly critical of employees, rate of advancement. And so the idea is we can hopefully fit a linear regression model to all of these variables, but maybe not all of them need to be in there. So that's going to be the question I'm going to be coming at today. Now, I want to say when we do variable selection, I am really viewing it through the lens of regression analysis for understanding. I'm curious about which of these variables really are potentially important if I'm thinking about predicting sort of which managers are going to be popular with their employees. What variables do I think might actually be meaningful here? I am not going to be thinking in terms of statistical inference. I'm not going to be trying to make confidence intervals or do p-values in the inferential sense. I'm going to be using them more for deciding which variables to keep in. One other disclaimer I want to say here is even though I'm going to be doing backward stepwise selection here and doing some model selection and variable selection, I want to discourage you from ever doing this mechanistically. I think this is useful to us as we try and understand the data, the relationships between the variables. If you try and do this mechanistically, the models that you get out of it are potentially going to be problematic in any number of ways. So let's get started with this. First of all, I want to make sure that a regression analysis is even potentially warranted here. So the fundamental assumption of linear regression is that there's kind of a linear relationship between each of the explainers and the response variable. Now, linear regression is going to be robust against some violations of that, but if there's not a fundamentally linear regression, we need to ask, why are we trying to do a linear regression on this? So a nice function, I think, in the Galley package that I use a bunch on smaller data sets like this is the ggpairs function. And all you need to do is pass it the name of the data set. And now we're going to get a matrix of plots between all the different pairs of variables. And since these are all quantitative variables, we're going to have a scatter plot for each of the pairs of unique variables. It'll take a second because we're getting a bunch. I'll zoom in on that. Okay, so the response variable I'm interested in is overall rating. You can see I've got just a density plot here for overall rating as a single variable. That's where it intersects with itself. And then the other 6 are going to be overall rating versus each of the other individual variables. And as I glance at these, I don't see any major violations of the linearity assumption. In some cases, there really does look like a specific linear relationship. Other times it's a bit more cloudy. Again, I don't mind if there's a little bit of a curve, but if everything is totally smashed to one side or everything is much more complicated in its shape, I want to think about doing some pre-processing or selecting a different modeling method. All right, as it is, I think I'm okay doing a regression analysis. So the idea of backward stepwise selection is that I'm going to start with a full model. In other words, I'm going to take every one of those 6 potential explainers and put it in a linear regression model for my response variable. And then I'm going to take the variables away one by one, in each case taking the one that seems to be the least significant in the model or the least useful in that model until I get to some predetermined stopping criteria. Now, there are a lot of different flavors, both for the selection method, how do I decide which variable to keep and which one do I decide to throw away, and the stopping criteria. These are both choices you have to make as a data scientist and as the person doing the regression analysis. So at the beginning, I have to make a choice. And I'm going to use the t-statistic. I'll use the t-statistic to decide which variables to throw away. Let's make that singular, which variable to throw away at each step. And so I'll be throwing away the variable that has the smallest t-statistic at every step. That's not the only way. It's not necessarily even the best way, but it's certainly I think the easiest one to see here in R, and it's a good way to understand the stepwise selection process. So that's the one I'm going to use today. If I were doing it on my own, I would probably use Akaike information criteria, although even that can be controversial at times. When do I want to stop? So here I'm kind of deciding how liberal I want to be about leaving variables in my model, or to say it the other way, how stringent I want to be about keeping them. So in other words, am I okay with variables that have a little bit of a chance of being statistical noise? The trade-off of that would be that I would probably have or almost certainly have a better fit to the data that I actually have. So do I want to lean more towards bias or towards variability in that bias-variability trade-off? So I'm going to be pretty liberal about what I keep in. So I'll keep going as long as I have a t-statistic under 1. And that's a criteria I've seen by several authors. Again, this is a very liberal criteria. I'm going to end up with more variables here than I would with using other criteria potentially. But this is one that I've seen used by several authors. So let's start just by getting the full model. And I think I'll call this model 6 because it's got 6 explainers, and that way I can be consistent with my naming conventions. I'm going to be using the linear model function, LM. First I say the response variable, the thing I'm trying to explain, so that's overall rating. Then a tilde, and then I would say each of the variables that I want to be an explainer separated by a plus sign for a regression without interaction. So I could do handles employee complaints plus no special privileges plus space for learning, etc. Now that's going to get to be a lot of typing very quickly. Doesn't make for good YouTube. There's a nice shorthand. I can just do a dot, and that'll use all of the explainers in exactly the way that I just described. Every variable in the data set except for the one on the left-hand side. I do have to let R know what data set I'm looking at, so data equals performance. There we go. And we can just see a summary of that model. Let me resize my window before I execute that. Oop, model 6, not model. Okay, there we go. All right, so we have estimates for all our coefficients. So this model looks like 10.79 plus 6.1 times the value of the handles employee complaints variable, minus 0.07 times the value of the no special privileges variable, and so on. So if you had a new observation in this data set, you'd have values for all these variables. You'd plug it into that model. You'd get a potential prediction for the overall rating that they would be assigning to that supervisor. Okay, so for this kind of analysis that we're doing, where we're just trying to understand these relationships, trying to decide which of these variables might not actually be so useful to us, we are going to look at the t-statistic here, the t-value. So remember, the t-statistic here is giving you a measure of how surprising or how far away from, let me start that sentence again, of how surprising the coefficient that we got would be if we got it just by random chance, if in fact in the population the coefficient were 0. So for instance, in this case, from the data, the coefficient of handles employee complaints has come out to be 0.61 based on the sample data. If the coefficient from the population were actually 0, How likely would it be to get something like this? The 3.8 is saying that this is fairly surprising. The p-value is quantifying that in terms of a probability. The probability of getting a t-value at least that large, just by random chance, is 0.0009 approximately. So t-values that are closer to 0 are giving the weakest evidence that the variable, that the coefficient, the regression coefficient, is non-zero. So in this case, the weakest evidence is coming from the not overly critical variable. And so I'm going to want to remove that from my model. Again, the idea is that at every step, I'm going to remove the variable that has the t-statistic that's closer to 0. I'm going to keep going until I no longer have one that's smaller than the cutoff that I set, which was t equals 1 in absolute value. So I want to make a new model. Let's call it Model 5. I could do a LM from scratch, overall rating, tilde, and then actually put in all 5 variables. But there's a handy function here in base R. It's the update function. And update takes the name of the model that we're updating, Model 6, and then we have to say something about how to update it. So I'm going to put in the model notation again, this tilde kind of thing. And if I just put dot tilde dot, that means keep everything that you had on the left side related to everything that you had on the right side. And so by doing plus a variable or minus a variable on either side, I can update the model formula that I already had. So in this case, I want to take out not overly critical, which you'll see that I've copied and pasted. So take the right-hand side that I already had and take out the not overly critical variable. And if we do a summary on that, you're going to see that now our model only has 5 variables. And you'll see that not overly critical is no longer in there. Now, if you have some experience doing regression models in R, you'll know that there's a lot of other ways to do the stuff that I'm doing. In particular, I am definitely doing it a little bit longhand. I want to talk through this, try and do it for understanding more than for sort of computational efficiency. Just trying to get a handle on backward stepwise selection to see how it works. Okay, so if you look, you'll notice that the t-statistics have changed even for the variables that we've kept in. So for instance, raises for performance had a t-statistic of 0.369. Now raises for performance has a t-statistic of 0.470. So it's moved away from 0. Now that we've taken out that other variable, this one has just a little bit more relative importance. So this is part of the reason that we are only taking out the variables one at a time and recomputing every time. Because, of course, even though our model doesn't have interaction, these variables do help explain one another. All right, so now we again repeat what we did before. We see that raises for performance has the next smallest t-value, so we're going to take that out. We'll call this Model 4, and we'll update our model. Update Model 5. And again, dot tilde dot, ooh, typing, very bad, dot tilde dot minus raises for performance. In my defense, it's late at night when I'm recording this. I get sloppier as the day goes along, I'm afraid. And I'm updating Model 5, not Model 4. All right, so summary of Model 4. All right. So let's see here, make this a little bit more console friendly. Great, so we've got one more variable here that I'm concerned about, no special privileges, still has a t-value that's pretty close to 0. So let's take that out. I'm almost done with the repetitive part of this. We'll get on to some more interesting things in a second. So Model 3, update Model 4, and dot tilde dot minus no special privileges and summary of Model 3. Okay, great. A little bit wider there to actually see it. Okay, so now our t-values are all over 1 in absolute value. So our stopping criteria has been met. I'm not going to go through and take out any more variables. Now, if you remember earlier on, I said that I was being pretty liberal. I was going to be pretty liberal about what variables I left in this model. So, in particular, you can see that rate of advancement still here still has a p-value of over 20%. In other words, even if that coefficient were actually 0 in the overall model, we would still get results as extreme as this for our coefficient of rate of advancement a little more than 20% of the time. So it's not a hugely high bar for keeping in that variable. What this is doing is giving me a better fit to my data, potentially at the expense of greater variability. If I were to go out and get more sample data, I might have some larger differences in my model than if I were to leave out this variable from my model. So that's a data decision that I've made. In this 3-variable model, the other two of these other variables, well, intercept I guess will always have the intercept in there, but this other variable, space for learning, also has a kind of marginal p-value of 0.05. So it also wouldn't be radically surprising if that coefficient were 0. Okay. Now that we have a final model, I want to get a diagnostic plot. I want to get a residual plot. We could use plot model 3 to get 4 different diagnostic plots, be a bit more thorough using base R. I think I just want to get a residual plot. That's kind of quick one-stop shopping for your model diagnostics. You can see most problems in a linear regression model from a residual plot if you don't need to be too overly worried about your assumptions being exactly met, which is most of the time. In order to do that, I want to use the augment function from the Broom package that I'm a big fan of. So this is going to give me a data set back. The data set is going to be an augmented version of performance. So I'm going to call this perf_aug, I guess. And I'm going to do augment. Again, that function is from the Broom package. And the argument I need to pass it is the name of the model. So here, just my final model, model 3. Let's take a view of that, perf_aug. There we go. Okay, so we've got the variables from the original data set that are in our model, in this case, all of them, as well as a number of other pieces of information corresponding to each observation. We have the fitted value, the value of the response variable as provided by the model, the residual, how far our actual value differs from that prediction, and then several other things that tell us things like leverage and sort of how far they are away from the prediction in a more standardized kind of way. IOVIDs on each of those different columns. I'll get to that eventually. So the nice thing about this is now we can get a residual plot using ggplot as opposed to base R, which I find preferable. Perf_aug is the data set. And for a residual plot, we would like to do fitted values on the x-axis. It's dot fitted. And on the y-axis, we'd like dot resid. And then we just need a geom point to start. It can also be helpful to put a geom h line with a y-intercept of 0, just to show what just to highlight that x-axis. Let's zoom in on that. Okay, so in this case, if in fact the linear model is appropriate, we should basically be seeing a cloud. We shouldn't be seeing any patterns. We would like to see the spread be even as we go from left to right. We are seeing that. We would like to see that the original, let me say that differently. We would like to not see any particular shape to this. We don't want to see a parabolic shape or some sort of cubic shape. The idea being that the residual plot is more or less the pattern in the data when the linear relationship has been subtracted out. And if the linear relationship is really capturing the true trend in the data, then we shouldn't be seeing any relationship here. And so this is looking pretty good. I think the last thing I want to do is to ask about the AIC, the Akaike information criteria between these different models. So how does AIC compare between these models? So the Akaike information criteria is a measure of the model fit that imposes a penalty for additional variables or additional explainers being included in the model, as opposed to something like an R-squared statistic, which always improves when you add explainers, even if those explainers are just random noise and aren't actually doing any explaining. The AIC will start to get worse if you start adding in noise variables. In general, smaller numbers are better for the AIC. They tend to get more negative. So what I'd like to do is to get the AIC for each one of the models that I have. There's any number of ways I could do this. I could use a map function from the per package, as well as the glance function from the broom package. I think I'm going to do this just using an lapply and the extract AIC function from base R. So again, in keeping with the sort of like more basic perspective that I'm trying to bring to this video today. So let's make a list of all the models I have. And it's just going to be a bit of typing. I want model 6, I want model 5, and so on. The idea being I'm going to apply the same function to all of these. So 6, 5, 4, and 3, and that's where I stopped. And then let's apply, using lapply, to every element of the list, model list. Let's apply the function extract AIC, which is just going to literally take a linear model and give back the Akaike information criteria. And the printout here isn't going to be the most tidy. That's the downside of doing it this way. We have to remember sort of which element of my list here corresponds to which model. But this is a smaller case, so I know the first one is model 6, 123. The second one is model 5, 121. I think I said the AICs were going to be negative. That was a lie. I apologize for that. But smaller does mean better here. And so we can see that as we start removing the variables from the model, even though we're carrying less information into our model and getting a worse fit, we're also relieving the penalty that's imposed for additional explainers, so the AIC is going down, so that our model has gotten better. Fabulous. So we've seen a few different reasons why this model with 3 variables would be preferable to the model with 6 using backward stepwise selection.